Hi class, here's another question requested by one of you, question 9.40. And in this question, I think that what the diagram is given to you is to find out the maximum power transfer for the amount of the G impedance you have to find out, and then how much the power can be transferred. So to simply put this, then you have to deal with a lot on the voltage open circuit voltage and then the Thevenin equivalent circuit for this from this two terminal. And I'm trying to highlight here, convert into this form where you see that H Thevenin equivalent circuit is actually the part that you have to view from this terminal, and then you have to see if whatever the information has to be short and open based on the corresponding sources in the figures. So in this case, you have the current source and then a voltage source. So eventually, when you find out the V load will be equivalent to the Thevenin conjugate in order to have that kind of maximum power output, and then the voltage source has to be an open circuit in this case. So to move forward to the next step, I think I will pick to find out the voltage open circuit voltage for this circuit. So this will be the new diagram that you have to draw. So I will have to find out the voltage open circuit voltage at this terminal 2 and 3, and I'm going to label them 1, 2, 3 in this case to find out what would be the voltage, and as you know, this is a nodal analysis. As a result, you need to have the KVL written in the form that to describe the variable of the circuit. So let's start with variable equation, first equation. So at node 1, you can easily write this as V1. This is 1. V1 minus V3 in this case divided by 2, which result in this term. And then the second term will be V1 minus V2 divided by the resistor across that. So you have this second term V1 minus V2 over V2, which is a 2 ohms here. And then going out this way, you have 4 amperes constant. But as I said before, I like to move all the constant to the other side, which is the right hand side in this case. That will go from positive 4 amperes to negative 4 amperes. And what we need a little bit of reorganizations here to make this in a pretty form, and the next step is actually V1 minus V2 minus V3 equal to minus 8 in this case, that form the first equation. The second step will be find out the second equations, right? So same thing apply here. You look at this node and you sum out all the current going out from that node. That's got to be equal to 0. So V2 minus V1 divided by 2 ohms in this case, and then so this is a term that we have V2 minus V1 divided by 2, V2 minus V1 divided by 2, and then the V2 minus 0 in this case, because this is a reference that we are dealing with, divided by minus J2 because across that capacitors equal to 0, because that's the only two term. 1, 2, 1, 2. Reorganize this a little bit, that you have a minus JV1 plus minus 1 plus J bracket times V2 equal to 0. How do I know this is 0? Because there's no source that we're dealing with. Everything is just the variable here, equal to 0. So that's pretty straightforward. And one thing I didn't tell is that V3, in this case, when you look at V3, which is at this node, and you will realize that actually V3 is 6 volt in this case. So what I am going to do now is that instead of 6, so V3 is equal to 6 volt. Instead of having 3 equations, 3 unknown, 3 variables, I think that we can reduce that into 2 equations. So the only thing that we have to deal with right now is actually the first equation, the V3, substitute with the 6 volt constant here, and then move everything constant to the right hand side, and that's what I'm having here, is that 2V1 minus V2 equal to 2 minus 2. That form the third equation. Now we don't care about the first equation anymore because we are substituting the V3 into the first equation. So what you care about is that organize this second equation and the third equation and put it into the matrix form, which is here. So let's see if what I'm writing here is correct. You have 0 minus 2, 0 minus 2, okay, and then minus J minus 1 plus J minus j minus 1 plus j. So that corresponds to v1 and then v2, v1 and v2. So the first row and the first column for the x is actually correct. Let's see the second column, second rows. So the second row will be 2v1 minus v2. So we have 2 minus 1, v1 v2 v1 v2, and then the minus 2 here, minus 2 here. So this is a pretty organized format of the matrix that we know what we are going to find out. So in this case, we're going to find out the voltage on your right hand side, v1 and v2. So to do that, you have to, as I usually use the basic linear algebra variable as v equal to a times x. So in this case, you have to inverse the a. So inverse of a multiplied by b will give you the x. Why do we have to get to the inverse of a first? Because it's a square matrix, 2 by 2 side of matrix. So if you put b first and then time a inverse, you will have a dimension problem. So you have to use a inverse first, which is a 2 by 2 side of a matrix, multiplied by b, which is 2 by 1 of a matrix. As a result, you get 2 by 1 of the matrix as v1 and v2. So this is pretty straightforward. v1 and v2 equal to this 1.26 with a degree of 161.57 degree. Same thing for v2, 0.89 with a degree of 116.57 degree. So to find out the voltage of the VC, basically is a v2 minus v3. How do I know that? So the voltage open circuit here is actually v2 minus v3. How much the difference will be? So this we already know the v2 from the solver. Basically this is the v2, 0.89 with a degree of 116.57 degree minus 6 with the degree of 0, which is already given in the example, 6 with 0 degree volt. So so right now you have found what is required for voltage. This is a open circuit voltage, which is part of what we are trying to find here, right? So the next step will be find out the Thevenin equivalent impedance information. So let's go again, and what I think I did was I copy the whole figure and put it right here and label it in green to show the emphasis of what we are going to find out. So you're actually looking at the ZT Thevenin equivalent circuit and open the current source, short the voltage source. I repeat, open the current source and then short the voltage source. So in this case, you have open circuit and you have short circuit. You can reorganize this circuit into this configuration. How well, sometimes if you don't know what you're doing, it's better to be careful. And what I do, be careful. In this case, you have one terminal connected to 2, one terminal connected 3. So connected 2, connected 3, and 2 connect to a capacitor which connect to the 3, right? So that's in parallel with the minus j2 ohm, and then 2 connect to the 1, 2 connect to the 1 with the 2 ohms, and then 1 connect to the 3 back again, 1 connect to the 3 back again, which is 2 ohms. So you can see that this is actually 4 ohms resistor in parallel with the minus j2 ohm. In this case, which will lead to the next page would be 4 times minus j2 divided by 4 minus j2, that give you 1.79 with a degree of minus 63.43 degree ohm. This is in the polar form, or you can choose to write in the rectangular form, which is 0.8 minus j 1.6 ohm. So this information, G Thevenin, actually is found. So you have the G Thevenin, and then the G load is actually G Thevenin conjugate. So that's basically, you only found one information. You don't have to repeat the whole process. But in this case, you can simply change the sign, which is a highlight in the red colors. So this is actually, instead of having the minus sign, you have a positive sign for Z load. So put this in the contents and solve by the basic circuit. So in order to find out the current here, why do I care about finding current? Because we want to find out the maximum power transfer. If you know the voltage, you don't know the current. So let's find out the current here, because the maximum power transfer is actually depends upon how much the load impedance will be, which we just found here, which is Z Thevenin of the conjugate. So to find out the current going around this loop, which is a V open circuit divided by Z total impedance, which is Z Thevenin plus Z Thevenin conjugate. And we found V over open circuit and divided by this total impedance, which is Thevenin plus Thevenin conjugate. We have 6.45 with a degree of 172.91 divided by the total. And be careful about the sign here. You have minus, you have a positive sign here, and the N outs to be 4.03 with a degree of 172.91 amperes. So we're not quite done here yet. So we have to find out the maximum power, which is I squared times R divided by 2, and then plugging this magnitude information into this equation, and you'll find out the maximum power transfer is 6.51 total. So if you recall, how do I apply all this equation and all that, you may go to the page 443 from the textbook, section 9.3, and on that page all the way down to the bottom there's a problem solving strategy indicating about the maximum average power transfer from step 1 to step 3, and the Z load is actually indicated as Z Thevenin conjugate on step 3. And then to find out the maximum power transfer for the average of them is either the half times I squared times RL, or the V squared open circuit divided by 8 times the R Thevenin equivalent circuits. So that's the reference for you if you wonder how this equation would apply, which is coming from the page 443 from the textbook. Hope this helped. Thanks.